Hello and welcome to our ICE Engine Week 1 presentation. My name is Tuelo, along with Micah and Patrick. As Bedell Inc., we've been hired by Generative Energy Systems to determine system parameters and control for a new IC engine. IC engines generally involve thermodynamics, fluid mechanics, and heat transfer processes. There's a need to understand the mechanical and fluid properties of these engines as well as the control dynamics to fully characterize such systems in order to optimize the performance and power generation in cases where energy recovery is important. The main objective for us is to develop system parameters and controls for a generator based on a modular IC engine to optimize power generation. To start this process, a work energy model is to be constructed. And to do this, the mechanical system was characterized first by finding properties such as the work done by the motor on the engine. In future, the fluid system and the control system will also be characterized to get a full model of the system. Here's a system outline, and it consists of a single cylinder, four-stroke reciprocating piston engine that is connected to a 48-volt regenerative motor with a force transducer. This is all connected to a data acquisition module, and we use MATLAB for data processing. To calibrate the force transducer, weights of a known mass were placed on the transducer at a known distance. And in order to build the work energy model, quantities such as frictional torque and moment of inertia of the flywheel were isolated and determined independently. This experiment was ran at 3 operating speeds on a system with 4 flywheels under steady state and transient conditions for each speed. Flywheels were used to reduce fluctuations in the output angular velocity and to store energy. A repetition of this experiment was done with 1 flywheel, and from here, the calculated and derived quantities were used to construct a work energy model for the operation of the IC engine.
The torque sensor was calibrated for each of the experiments that were done. The uncertainty of the gain and offset are relatively low, and this contributes to the validity of our results. The combustion engine can be characterized using the sum of work that is impacting the system, and as well as the kinetic energy change from the beginning and from the end of when the system is changed. We will sometimes take advantage of this when we're talking about energy coming from a steady state to allow the change in kinetic energy to be zero. We will also use it for other ways to cancel out that first term. Here's an equation that we use to calculate for the energy at the start of a system. When we're starting from zero, there's zero angular velocity, and so that term, the E fly A, goes to zero. Also for steady state, these come to zero. Here's the work contributors that are on the other side of that equation. You've got components from the motor, air, friction, and piston. The reason why the work from the motor is negative is because it comes from an outside source. So here is this equation. Here's how everything fits into it. We assume by taking the head off, we can assume that the work done by air is zero. Additionally, the work from the piston cancel itself out because it's an oscillatory motion of work being in and taken away. Additionally, and after making this steady state assumption, and collecting data after the system has already started, we can equate the work of the motor to the effects done by friction. So here's a result of these data collected from here. We integrate the torque across the angular position, and we're able to get the works done by friction. Here are the works in the top right corners done at each angular velocity, and we can see that they're relatively similar. And as engine RPM increases, the frictional torque increases in magnitude, indicating that the engine follows the Newtonian friction model. Uncertainty for motor work is 0.6714 joules. So far, as a little update, we've canceled out air. We've said that W work from the piston cancel itself out. We know the motor, we know the effects of friction, and we know the angular velocity. So now we're just trying to solve for the inertia. To find inertia, here's the equation. When we start from zero, that initial energy term is zero. So by rearranging these numbers, we can solve for I fly. Here is the torque values from when we start from 0 and we ramp up and we go to a steady state. Those work contributions are noted, and we use the same method to solve for these as we did in the previous plot example. The theoretical inertia of one disk is 0.0019, and we were able to calculate the inertias at using different wheel setups and at different speeds. We can see that the 4-wheel fly is definitely larger than the 1-wheel fly inertia, and this validates our assumptions of the way that inertia is working in the system.
So for future experiments, we plan to isolate both the work of air and the work due to from the piston. In our second experiment, we plan to reattach the head, which means that the work of air will no longer be 0. While there will be no air being injected into the system, the air inside will still be compressed and expanding. The goal will be to determine what that work is and then compare that to our theoretical value for work of the air, and then from there, look at our uncertainty and determine the validity of our model. Finally, in our third experiment, we will inject pressure into the IC engine to simulate the internal combustion portion of the engine, and ultimately with the goal of maximizing the engine output while minimizing the required motor input voltage. So the way we will analyze the work done by air is isolating what each individual stroke does. We'll run the motor for multiple iterations, and from there we will isolate and use multi-sample averaging to cancel out the noise. And from there we can get an idea of what each individual stroke represents on the velocity versus position graph. One thing to note here is the velocity is decreasing during the compression cycle, while it is increasing during the ignition or the power stroke. While velocity is useful to look at, it's more useful to look at the torque, and particularly the torque of the motor. Notice that the magnitude of the torque is increasing. This is negative. It's negative work, but it's increasing during the compression, suggesting that the motor is working harder, while it is decreasing during the power stroke or the ignition stroke. So from there, we are able to integrate the torque versus position for each stroke and calculate the value of work done by air for each stroke. And we can compare that to our theoretical model and calculate the uncertainty. And any differences between the theoretical and experimental will be anything that we did not model in our initial assumptions. In our final experiment, we are going to analyze the work done by the piston after determining all the other variables. And then with the goal being that the work with piston will no longer be 0 once we are inputting the air to the system. And from there, we are going to isolate and determine the parameters that will maximize the output energy while minimizing the input voltage required.
After finding the work energy model of the mechanical system, verifying how closely iFly for our model approximates iFly theoretical, and examining reasons for the discrepancies, the model can be considered valid. After the second experiment, work done by air can be calculated and analyzed, including the uncertainties. After the third experiment, the optical parameters will be determined to maximize power output while reducing input voltage.